Hello, myself Dr. Sudha from Government Science College, Autonomous, Bangalore. Today's topic is particular forms of Euler's equation. Let us recapitulate Euler's equation. Euler's equation can be stated as the necessary and the sufficient condition for the integral I of y is equal to integral x1 to x2 f of x comma y dash dx, where y of x1 is equal to y1, y of x2 is equal to y2 to be an extremum, that is either maximum or minimum, is that dou f by dou y minus d by dx of dou f by dou y dash equal to 0. In the previous session, we have seen that alternate forms of Euler's equation have two alternate forms. The first one, dou f by dou y minus dou square f by dou x into dou y dash minus dou square f by dou y into dou y dash into y dash minus dou square f by dou y dash square into y double dash equal to 0. The second alternate form is d by dx of f minus y dash into dou f by dou y dash is equal to dou f by dou x. We are going to use these two alternate forms to get the particular forms of Euler's equation. In this session, let us see the particular forms of Euler's equation. The first one is when f does not contain x explicitly, that is, f does not contain x. F is independent of x, that is the function f does not contain x. When it does not contain x, dou f by dou x, the derivative of f with respect to x becomes 0. So we have the Euler's alternate form, that is the second alternate form, d by dx of f minus y dash into dou f by dou y dash is equal to dou f by dou x. But dou f by dou x is equal to 0. So the right hand side becomes 0. So we get d by dx of f minus y dash into dou f by dou y dash equal to 0. Derivative of this function is equal to 0. Therefore, it must be a constant function. Therefore, we get f minus y dash into dou f by dou y dash is equal to constant. So, let us take that constant to be some k. So, whenever f does not contain x, the Euler's equation can be written as f minus y dash into dou f by dou y dash is equal to a constant k. So this is the first particular form of Euler's equation. Now let us see the second particular form of Euler's equation, that is when f does not contain y. When f does not contain y, that is f is independent of y. So the derivative of f with respect to y becomes 0. So we have the Euler's full form, that is the Euler's equation, basic Euler equation, dou f by dou y minus d by dx of dou f by dou y dash is equal to 0. So here dou f by dou y is 0. The first term becomes 0. So we get d by dx of dou f by dou y dash is equal to 0. So derivative of this function dou f by dou y dash is equal to 0 implies that dou f by dou y dash is equal to constant. Let us once again take that constant to be k. Therefore, whenever f is independent of y, that is f does not contain y, then we can take the Euler's equation to be dou f by dou y dash is equal to a constant k. So this is the second particular form of Euler's equation. Now let us move on to the third particular form, that is when f does not contain both x and y. When f does not contain both x and y, that is when f is independent of both x and y, the partial derivatives of f with respect to x becomes 0, and the partial derivative of f with respect to y also becomes 0. So when the first order partial derivatives become 0, the second order partial derivatives, that is dou square f by dou x into dou y dash is equal to 0, dou square f by dou y into dou y dash is equal to 0. So now let us consider the other Euler's alternate form, that is the first alternate form, dou f by dou y minus dou square f by dou x into dou y dash minus dou square f by dou y into dou y dash into y dash minus dou square f by dou y dash square into y double dash equal to 0. So let us substitute the values of dou f by dou y, which is 0. Dou square f by dou x into dou y dash is also equal to 0. Dou square f by dou y into dou y dash is also equal to 0. So we are left with the term dou square f by dou y dash square into y double dash is equal to 0. So when this term is equal to 0, we can take y double dash is equal to 0 provided the partial derivative of f with respect to y dash is not equal to 0, because f will be a function of y dash alone. So we can take this not to be equal to 0 implies y double dash equal to 0. When we integrate this twice, we get y is equal to ax plus b, where a and b are constants of integration to be the solution, and this solution represents a straight line. Y is equal to ax plus b. So this is the third particular form of Euler's equation. So hope everybody followed the particular forms of Euler's equation. In the next session, we are going to solve problems related to these particular forms.